All right, so get ready, because today we are diving deep into some pretty heavy physics. We're tackling a question that I think will really kind of blow your mind. Is space-time even real? Or could it be that it's just some kind of crazy illusion? We're going to be looking at excerpts from this article called, Is Space-Time Just an Emergent Quantum Energy Field? And as you can probably tell, this article is suggesting that maybe things are a lot weirder than they appear.
I think what's really interesting here is that this idea really challenges how we tend to think about the universe, right? We're so used to thinking about space and time as being kind of the stage for reality, the fixed backdrop. So what if instead this backdrop that we're so used to is actually something much more dynamic, something that's emergent?
Right. It's like finding out that stage is all holograms, right?
Yeah.
But before we get too far into all that, let's actually start with what we think we know. So Einstein, he gave us this picture of space-time as this kind of flexible fabric, right? And it bends under the weight of mass and energy. And this bending is what creates gravity. Pretty straightforward, right?
Seems like it is, yeah. Until you start to zoom in really, really far into the subatomic level. Now we're getting into the quantum world, and quantum mechanics comes into the picture.
Wow.
And what we find down there is that space-time isn't so smooth and simple anymore. It actually becomes incredibly chaotic and unpredictable. You can kind of picture it as if the fabric starts to fray apart at the edges. So now we have this clash between general relativity, that's what governs the large-scale universe, stars and planets and galaxies, and quantum mechanics, the rules of the microscopic world. This clash creates a huge headache for physicists.
Right, because on the one hand, you have Einstein saying, okay, space-time's smooth, curved sheet. And on the other hand, you have quantum mechanics basically going, nope, down here it's all fuzzy, it's uncertain.
Man.
These two things don't really go together, do they?
Not really, and that's exactly why physicists are now exploring different theories, alternative theories. One of the most interesting and mind-bending of these theories is the idea that space-time itself is not actually fundamental, but it emerges from something deeper. And that deeper thing is quantum entanglement.
Okay, see, now we're getting to the really trippy stuff. So just as a reminder for those of us who might need it, quantum entanglement is this phenomenon where you have two particles.
Yeah.
And they're linked together in this really bizarre way. No matter how far apart they are, it's like they have this invisible connection that lets them share information instantly, even if they're on opposite sides of the universe.
Yeah, it is super bizarre. And what's even more wild, I think, is that this entanglement might actually be the key to how space-time comes into being in the first place. So imagine this. A vast network of entangled particles constantly sharing information across these distances that seem impossible. Now, some physicists think that this network of entangled particles, is actually the true fabric of reality. And what we see as space-time is just a kind of projection of that network.
Whoa, okay, hold on, slow down for just a second. So you're saying that instead of thinking of space as this empty container and time as this steady river that's always flowing forward, we should actually be picturing this giant network of entangled particles. And this network is what's creating space-time.
Exactly. It might help to think about it like a video game. The world you see on the screen, that 3D world, it's not really 3D, right? It's actually created by a 2D program that's running in the background. So that 2D program is the underlying reality, and the 3D world that you experience is just a projection. In the same way, our 3D universe could actually be a projection of this underlying network of entangled quantum information.
So space-time is the game and entanglement is the code. That's a pretty big shift in how we see things. It's definitely a pretty radical shift in perspective. But I still have questions. Like, even if this is how it works, if entanglement is creating space-time, what's the actual mechanism behind it? How does that actually work?
That is a great question, and it's what a lot of physicists are trying to understand. One of the most intriguing ideas out there is this concept called the EPR conjecture. Now, stick with me, because this is where things get really, really interesting.
Okay, I'm ready. Hit me with this EPR conjecture.
Well, this has to do with wormholes, those theoretical tunnels through space-time. They're like a science fiction staple.
Yeah.
But the EPR conjecture is saying that maybe wormholes aren't really tunnels through space-time at all. Maybe they're actually manifestations of entanglement.
Hold on. So you're saying those shortcuts through space and time that we see in movies, maybe those are actually just entangled connections between different parts of the universe. So like those two entangled particles that we were talking about, maybe they're actually connected by a wormhole.
That's the idea. And if it's true, it has some really, really big implications, because it would mean that space-time, it's not this smooth, continuous fabric like we always picture it, right? It's actually more like a network of points. And those points are all connected by entanglement, like threads that are weaving them all together.
Okay, that's wild. I mean, if that's true, it changes how we even think about the idea of distance. But how could we ever prove this? I mean, are there experiments that we can do to test this?
There are some people working on some really ambitious experiments that could test it, but before we get into those, I think we need to explore another piece of this puzzle, something called quantum error correction.
Quantum error correction.
Yeah.
How does that fit into all this?
Well, it's a concept from quantum computing, but it might actually help us understand how space-time can stay stable, even though it's built on this foundation of quantum mechanics that's all fuzzy and uncertain.
Okay, so back up for a second. I know a little bit about error correction in normal computers. That's how they prevent data from getting corrupted. But how does that apply to, like, the entire universe?
Well, think of it this way. If space-time is constantly emerging from this network of entangled particles, you're going to have a lot of randomness, right? Fluctuations at the quantum level. It's like this constant background noise. But somehow, despite all that noise, space-time seems really stable.
Yeah, that's true. I mean, if it wasn't stable,
Yeah.
everything would be constantly glitching, right? Reality would just fall apart. So how does this error correction come in?
The idea is that maybe the universe has this built-in mechanism for correcting those quantum errors. It's constantly smoothing out the fluctuations, keeping space-time nice and stable.
So it's like the universe is running a giant spell check, right? Is constantly fixing these typos in the fabric of reality.
That's a great way to put it. And some physicists think that this error correction is actually what gives rise to the laws of physics that we see.
Well, wait, so you mean gravity, electromagnetism, all the forces of nature? You're saying they're not just hardwired into the universe, they're actually coming from this error correction process.
Yeah, that's one of the more radical ideas. It means that the universe is a lot more dynamic and self-regulating than we might have thought before. It's not just a clock following some preset rules, you know? It's more like this self-organizing system. It's always adapting and correcting itself.
Okay, my brain is like officially doing backflips now.
Yeah.
So we've got entanglement that's creating space-time.
Yeah.
And then quantum error correction to keep it all stable. But where is all this information coming from? What's like the source code of reality?
That's the million-dollar question, right? And it leads to one of the most profound and controversial ideas in physics, that reality itself, at its most basic level, is informational.
Informational? Wait, you mean like it's all just bits, like a computer program?
Yeah, some physicists think that's exactly what's going on. They're suggesting that instead of thinking about the universe as being made of matter and energy, maybe we should think about it as being made of bits of information.
So instead of atoms and quarks, we're talking ones and zeros. It's like something out of the Matrix.
It does kind of, doesn't it? But, the idea actually has some support. I mean, just think about how quantum mechanics already blurs the line between information and reality, like particles existing in multiple states at once. That's like a bit that can be 0 and 1 at the same time. And entanglement, right, that allows information to be shared instantly across vast distances. It's almost like it's ignoring the limits of space and time as we know them.
So are you saying that space itself might not even be a fundamental thing? Maybe it's just a way to organize information? Like, what if distance is just a measure of how much information it takes to get from one point to another in this cosmic network?
That is a really interesting way to put it. And there's this mathematical framework that actually supports this idea. It's called tensor networks.
Right.
And these networks can model how space-time can come from these patterns of entanglement, basically showing how information can be woven together to create what we experience as space.
So it's like these tensor networks are the blueprints for reality. They show how information gets turned into physical space. But if all of this is true, it leads to a pretty wild possibility, doesn't it?
You're thinking about the simulation hypothesis.
I am. If the universe is really informational at its core, does that mean it could actually be a simulation running on some kind of giant cosmic computer?
Well, that's a question that a lot of people are asking, both scientists and, just regular people. And there are definitely some interesting parallels between how the universe works and how a quantum computer might work.
Like what? Give me some examples.
Sure. Well, as we've already talked about, particles can exist in multiple states at once, just like a qubit in a quantum computer. And entanglement that allows for communication that seems instant across huge distances, kind of like how data can be transferred in a quantum computer. And even some of the weird stuff in relativity, like time slowing down near massive objects. We could explain that as information processing being affected by gravity.
So instead of thinking about gravity as warping space-time, We can think about it as gravity messing with the flow of information.
Exactly. It's a big shift in perspective. But it might be the key to finally unifying quantum mechanics and general relativity.
Which is something physicists have been trying to do forever. But even if all this is true, right? If the universe is a simulation, wouldn't that just mean there's an even bigger mystery? Like, who or what is running the simulation?
That's a question that science might never be able to answer. But it's a question that makes us confront the limits of what we know and consider possibilities that are truly mind-blowing.
For sure. So we started by questioning if space-time is even real. Then we got into the idea that maybe the universe is just information. And now we're wondering if the whole thing is a simulation. It's a lot to process.
It really is, and it all comes down to this idea. That information might be the most fundamental thing in the universe.
Which is a pretty revolutionary idea.
It really is. It's opening up all kinds of new avenues for exploration. In physics, in cosmology, in how we understand the universe.
But what about time? Where does that fit into all this? If space-time is an illusion, does that mean time is an illusion too?
Yeah, that's a huge question, and it really gets to some of the weirdest stuff in quantum mechanics. Like, we've all heard about particles being in multiple places at once. That's superposition, right? But some people think it's not just where a particle is that's fuzzy. It's like their whole history might be too.
Wait, so a particle's past isn't even set in stone. It's kind of spread out like its location can be.
Exactly, yeah. In some of these models, a particle doesn't actually have one path through time. Not until it gets measured anyway. It's like all the possible paths are happening at the same time, and then when we look, all those possibilities collapse down to just one.
Okay, that IS weird. But I kind of see where you're going with this. If time itself isn't really fundamental, if it emerges somehow, then maybe cause and effect gets messed up too, right? Like that idea that one thing causes another in this nice, neat order. Maybe that doesn't work at the quantum level.
You got it. Some physicists are saying that what we think of as the arrow of time, going from past to future, that might just be a big picture thing, something that doesn't hold true in the quantum world.
So the quantum level, time is less like a river and more like, I don't know, a crazy ocean, where the currents can go any which way.
Perfect analogy, and that opens up some seriously wild possibilities. Imagine a universe where what happened in the past isn't even fixed, where stuff can influence each other in ways that seem to break the rules of cause and effect.
So basically, all our normal ideas about time and what causes what, they go right out the window. That's both exciting and terrifying. But how could we ever test that? It's not like we can hop in a time machine and check if the past is really that blurry.
Well, not yet, anyway. But there are experiments in the works to see how far we can push these ideas. Like trying to see if we can break something called Bell's theorem. It's all about how much entanglement can link up two particles.
So if they find even more linkage than that theorem says is possible, that means something weird is going on with time, right? Like our normal understanding is incomplete.
Exactly. It would be a huge clue that time is way more complex than we thought. Another idea is to use super accurate clocks to measure tiny, tiny changes in how time flows. See if there are any spots where it doesn't match up with Einstein's relativity.
So basically looking for those little glitches in the matrix of time, right?
Yeah, kinda. Trying to find hints that time isn't this smooth, unchanging thing we experience, but something much deeper. And maybe even just an illusion.
This whole deep dive has been one mind-blowing idea after another. First, we're wondering if space-time is even real, then maybe the universe is just information. And now we're saying maybe time itself is an illusion. My head is spinning.
It is a lot to take in, but that's what's so cool about pushing the limits of what we know. We're always discovering that reality is even weirder and more awesome than we thought.
So where do we go from here? What should our listeners take away from all this?
The big thing is, our understanding of the universe is always changing. What seems fundamental today might be just the beginning, a stepping stone to something even bigger.
It's like peeling back the layers of an onion, and every layer reveals something new and unexpected.
Exactly. And that journey is far from over. There are so many mysteries left to solve, so many questions to ask. That sense of wonder, that drive to explore the unknown, that's what makes science so captivating.
It's been an amazing journey talking about these ideas with you. So to all our listeners out there, keep asking questions, keep exploring, and never lose that sense of wonder. Who knows what incredible discoveries are waiting for us just around the corner.
Absolutely. The universe is full of surprises. And the more we learn, the more we realize how much we still don't know.
That's it for our deep dive into the mind-bending world of quantum physics and the nature of reality. Until next time, keep on diving deep.